Good afternoon, students. So, we will continue our discussion of low power VLSI design technique. Last day we just started about the introduction of the low power VLSI design. So, we will continue on that, and this is the VLSI design flow. I hope you all are familiar with this so far. So, we will start, generally we start with the design specifications. Whenever you start a design, you go with a design specifications, and then you start architectural design, be it in schematic design or RTL design. So, we have two kind of analog design flow or VLSI design flow. So, terminology wise this is the flow: specifications, then design, and this could be RTL coding or circuit design, then synthesis, and so this considered your front end, and physical design, layout, and those considered back end designs. So, physical designs, and when you go for fabrication, this is basically preparation of the GDS, and then you will send the GDS file for fabrication, and after the return of the IC with packaging, you will do the testing for final verification. So, in between, in each steps you will be having verification steps. I hope you all know that starting from top level, you will do a, for quickly you will do a top level simulation, right. So, just like that. So, in each level, suppose you are doing, you are at the you are at the early stage of your design. So, you are just defining your system. So, you will be having some specs. Then depending on the specs means maybe what is your frequency, what is your power, so what is your F, what is your P, and so on, what is your noise. So, depending on the specs, you will do a study, right. This is called the literature. I hope you all are familiar with these terms. First step is to, you will be checking that what are the available literatures in this domain and what are they doing. Depending on that, you will be selecting your architecture. This is your first step. Next is, suppose you got your, you have checked few papers and you have or few patents, and you decided that I will go with this architecture, and you started your design. Okay. In between you will be checking your specs, and when you are at the final stage of your submission, then you are seeing that these specs what you have achieved is not matching. Suppose your architecture is not proper, right, but by that time a lots of time has wasted, right. If you again go back for changing the architecture, it will eat up lot of your time, your design cycle time will be reduced. So, at each level it is better to verify it. So, in system level you will be doing some quickly verify, right. So, rather than going into SPICE level netlist verifications, it will take time if you have a bigger circuit. So, you will be doing top level or high level synthesis, high level simulations. For example, maybe you will be whatever the mathematics of your architecture, you code it in MATLAB or some other, maybe in Simulink, or maybe in SPICE you make it very top level, just define the mathematics and quickly check that if this system or this architecture is able to achieve the specs or not. Okay. So, that at each level you will be doing the cross check, so that you are not wasting a lot of time, and at the end you are getting that okay, this is not suitable, right. So, this is the generally the flow. So, for each level you will be having a verification. So, verification will be there at the each level, and this is the final verification at the silicon level. Okay, this is the proof, final proof, but on each level you should have a verification. If it is pass, you go to the next, otherwise go back to the previous. So, this procedure you will be following, and when you will be joining the company you will be following the, or you will be even in the R&D or PhD you will be following same flow. So, next is timing diagram. So, timing analysis, when you are doing RTL, you are doing ideal gate, right? You are considering ideal gate, there is no transport delay or path delay, but in reality when you will be doing, you have to check all the path delays, right, all the RC delays. So, your analysis apart from the gate, it will consider its self capacitance, wear resistance and the simulator. Actually, the simulator consider all of these and give you the realistic analysis. So, nowadays even for schematic simulation also there is an option for considering all these RC delays. In layout also, in physical design we have the, after layout we do a post layout simulation. In this post layout simulation we do RC extraction, RC. So, what is this? This physically, suppose you have a connection for A and B, these are just wire, right. Ideally they should have a 0 resistance, but when you are placing they will consider the resistance, parasitics, capacitance for all of this and will give you the final delay. Okay. Then you may need to, after the post layout simulation, you may need to edit your design. Suppose your frequency criteria is very stringent and your layout is poor, then you may have to go 1 or 2 more steps to edit the layout if your frequency criteria is degraded after the post layout simulations, okay, considering all the RC extraction. So, this is your front end and this is your back end. So, that we just discussed. So, this is our typical VLSI design flow. We have pre-layout simulation or schematic simulation, we have post-layout simulation, that is considering the physical. Okay. And in this post-layout simulation we will do the circuit extraction or parasitic extraction and we consider all the RC circuits and we combine them to get the tied. This is actually what we are doing, we are trying to have a feelings that after fabrication how the circuit will do. Okay. So, this post layout simulation is the most nearest simulation environment that you can have a feelings, okay, my after fabrication this could be my performance, okay, close to that. Even on top of that it will vary something. Okay. Okay. So, these are the logical design portion and this is your physical design portion, right, roughly this. So, in this you have design entry, logic synthesis, system partitioning. If you have a bigger block you can divide into partitions. In physical design you can have, first you have a floor planning, just like we do floor planning of our real estate, just in silicon also you have to do planning. Okay. Your silicon area is also as much as costly. Okay. When you go for fabrication, generally we book a area slab wise. Okay. So, we have a minimum area that we can book. So, floor planning, which portions will be placed to which position, placement, routing. Routing is one important aspect in considering the low power design, because when we are doing the design or when you are doing the RTL coding, we generally at the beginning we are not aware of what is the significance of routing, okay. But this may take appreciable amount of power, okay. A lot of power can be wasted here. For example, suppose you have a block something like that. Suppose this block and this block they have so many buses, okay. This bus they are individually bit some connections, and each of these for digital design, when we consider the VLSI design we generally you think that it is digital VLSI design, unless we talk about the analog VLSI design. So, this is we will be considering only the digital VLSI design. So, in VLSI design what is your swing? It is from 0 to VDD, right. This is our logic 0 to logic 1. So, you consider that each of these line they will be having some parasitic capacitance. So, they are going to charged and discharged fully, right, 0 to VDD. So, as much as this data will flip, this will be also having charging and discharging phenomena, right. So, all of these buses they will be having some parasitic loss due to this capacitance. Okay. Ideally when we consider, we do not consider the, even we do not consider the area for this routing, right, but this routing may take appreciable amount of area in your design. We consider this area, right. Interconnection may also be as much complex. If your design is very complex and having so much interconnections, so how we place, so we try to place whichever two block have more combinations, more connections, interconnections, we try to place them close to each. Otherwise, what will happen? Suppose this block and this block, they have lot of connections, but I am placing them away. So, I am unnecessarily increasing my area overhead, power, delay, everything. Okay. So, this will all come in this planning. So, unless you are at the final stage and you have a proper vision, so you cannot, at the very beginning you will not have, you do not have any guess of which block should be placed where, right. But as you progress, then you have to really plan about this placement, routing and flow. So, these are very important in back end design. In front end design, if you are doing only the coding, that is, suppose some designer is only responsible up to this. So, he will not know the complete flow, but in when you are doing the research or in an academics or you are doing PhDs. So, maybe generally one student will do the complete flow. So, he or she will be going through all of these design phases. Okay. In industry generally very few teams have the freedom to work in the all domain, they have a limited fixed domain, right. So, this is, as you will progress, you will be learning more about this, and in your final year MTech project also you will be working on this domain. So, you will be learning more about that. So, if we talk about the few major branches in microelectronics and VLSI design, you already know that one major aspect is analog design, next is digital design. So, in analog design also there could be, you have a requirement of low power design. Okay. In analog design generally we exploit sub threshold design, we try to keep the transistor in sub threshold so that power is less. For example, neuromorphic circuit design. Okay. So, or say biomedical, the ICs which will be used in biomedical applications, there we generally require very low power. Okay. So, for analog design also we have aspects of low power designs. In this course we will mainly concentrate of digital VLSI design, and if we get time we will explore the low power technique for analog design also. Okay. If we get time we will also explore this low power design technique for analog design. So, can you tell me just basic difference between analog design and digital design? What are the major differences in analog design and digital design? You see this linearity is an issue in analog design. Okay. In digital design we do not, this is non linear design. Now, next question comes, what is linear? So, for example, when your input and output are just y is equal to mx, these equations we can tell that it is linear. Okay. They are homogeneous and they follow the superpositions. If you use superposition, this will be satisfied, right. So, you see my input, this is my input, x axis is my input and y axis is my output. So, as input is progressing, output is also progressing, means if input is a sine wave, output will be also a sine wave, but this theta, this angle, this is called the tan theta is equal to slope or gain, right, m is equal to gain, right, tan theta. So, as this gets steeper, that means you are having more gain. So, if I give a sine wave, depending on my gain, I can have a gain of 1 or gain of 10 or whatever, right. So, this is my linear design, this is analog design. Okay. So, amplifier, data converter, PLL, reference generator, etc. are example of analog design. In digital design, I do not need, you see, you have a inverter, you give 0, you get a 1, So, it is getting saturated, right, it is maximum going to the max. This slope, you see, if you recall the inverter, this is the VTC of the inverter, right. This is input is 0, output is 1, input is 1, output is 0, right. But this is your linear phase. In analog design, you are working in this, right. Here you work as an amplifier, but in digital you are working in here, and in this phase you are having output 1, in this phase you are having output 0. This linear you are not interested, you say this as a do not care, right. If your input suppose your input is 0 to VDD, say VDD is 2 volt. So, when input is 0 you will be saying it is 0 volt, 0 logic, when input is 2 volt you will be saying it is 1 logic. But what will happen when it is VDD by 2? Will it fall in the 0 category or 1 category? You are not sure, right. So, this is you term that is metastability or X, do not care, so many terms are there, right. So, this is the terminologies that so in digital design it is linear, you have to take care that circuit is linear, and in digital design you do not need to bother so much about it, that if you are talking about MOSFET it should be in saturation in analog design, and it should be in linear and cut off in digital design. Cut off means 0, linear means 1. Okay. So, in digital design there are several structure like ASIC, full custom design, or semi ASIC, or FPD design, that is this programmable, this PLD or FPGA structure, where you have we are having some array like structure that we can program, okay, field programmable design, that is called field programmable design, that we will just very briefly we will discuss and we will move on. Apart from these two, so these two are our major branch. Okay. We are having a few subcategories like power management. For example, in mobile you have a dedicated power management, LDO, regulators, DC-DC converter, those sections. In RFIC design, RFIC means towards the this communications, transceiver circuit, receiver and transmitter circuit. Clock design also you can fall it can fall in RF design because it is high frequency. So, oscillator design, PLL design, this can also fall in analog design also as well, but application wise it falls in the RFIC. Okay. Another new domain is getting importance nowadays, that is called the MEMS, okay, circuit design for the MEMS interface. Okay. In real life applications, for example, airbag in or accelerometer. So, several micro electro and mechanical structure there, we are shrinking them, right. We are fabricating a mechanical structure in a silicon. Okay. For example, comb like structure for capacitive based accelerometer. So, it is also possible to fabricate them in silicon and reduce, our aim is to reduce the size, so that we can use them side by side with the integrator circuit, right. So, they are not as small as the ICs, integrated circuits, but compared to their mechanical structure they are much more scaled down. So, they will take very less area and may have applications in different wearable devices, gadgets, home appliances, car appliances, etc. Okay. So, this is a growing area. So, this is also coming in picture. So, this is our FPGA. So, generally you may have seen the FPGA board or you will be doing experiment in your laboratory. So, this is so that you can you can program and erase. So, repetitively you can use for several times. Okay. Suppose you have designed a microprocessor on your own. Okay. Now, you want to check that how it is doing. Now, if you directly go for fabrication, that is a one is problem is it is a lengthy procedure, and another is it is a costly procedure. So, as a student or as a academic person, we do not have that access for the budget, right. So, rather than going for fabrication which may fail, right, your design may fail, right. So, we need to verify it, that is it working well or not. So, one way to get the feelings of how it is behaving on the silicon is to test it on your FPGA board. So, this FPGA board, it is giving you so much programmability or flexibility, so that you can dump your design, check your output, and then if you are satisfied, you can go for maybe ASIC verification or ASIC fabrication, or you can redesign and again proceed. So, this gives you a platform for doing the trial and error. Okay. So, this is comparatively costly, because you can do several time testing, right. So, this is a bigger block where you have multiple CLBs. So, these CLBs are configurable logic blocks. So, each of these are configurable, even the connections, input output connections are also configurable. So, suppose you have some adder and then multiplier and then ALU. So, maybe you use some of the blocks of this block, some of the circuits of this block, some of the circuits of this block, and interconnect them, and your complete design is done. Next time you will be doing, maybe you will be using this block, this block. So, this is completely programmable. Okay. And as there are so many input outputs, these are all IOs. IOs means input and outputs. Okay. So, there will be some memory block, there will be some lookup table. Okay. So, you can implement anything, you will be having logic gates, you will be having PLA structure, array structure, and plane, or plane. Okay. So, any ever function, if you recall, if your K map, you could have represent them in sum of point function or AND of OR function, right. Two presentation was there, right. So, same you can. So, if you have a equation, that you can do it here using AND plane or OR plane. Okay. So, what is the advantage? Advantage is that you are now having the flexibility, reprogrammability, reusability. Okay. So, you can use this several times. Okay. And as this is already, so you think of this like a testing on a fabricated silicon. This is fabricated, just the interconnections are changing. So, your result are actually on silicon, right. So, that is the main advantages. So, now if you think that, then you may ask that, then what is the comparison between FPGA and ASIC, right. ASIC is application specific integrated circuit. If you compare the area of FPGA and ASIC, FPGA is so big because you have so much options, but ASIC could be very specific. So, its area will be very small, that is the difference. When you are sure about your applications, you have done all the experiment in FPGA and you are satisfied with your architecture, you go for fabrication, that is your ASIC. In FPGA there are so much area, right, so much redundancy. Redundancy means same block repeated. So, as same block is repeated, it is costly, is not it? Okay. So, you will be doing this and you will be learning this in your lab. So, no, do not worry. So, if you look at your smartphone, you will be having all of these applications. Starting from analog design, there could be amplifier. Starting from digital design, there is a processor. You have RFIC, you have antenna, okay, transmitter, receiver, and even there are MEMS compatible circuit also. Okay. Sometimes we have several gyroscope, accelerometer, so many things. So, this smartphone is a complete example of having all the major branches. So, this shows us the different component of the power dissipations. Okay. The subject, this is the main theme of our subject. So, I hope you all know that main two power dissipation, one is static power, another is dynamic power. These are main, right. So, can you please tell me what is static power? From the name, what you understand? Input is static. Static means input is not moving that much. Okay. So, for example, suppose your input is at 0 state and it is staying at 0 state. So, this is the example of a static power. Okay. And dynamic power, you can understand that it is moving from 0 to 1 and 1 to 0 and so on. Okay. Now, when we move from BJT to MOS or CMOS technology, you see, initially we were very happy. We thought that we have solved our problem. Why? Suppose your input is 0, input 0 means NMOS is off, right. NMOS, it should be above Vt of the NMOS, then only this will turn on. So, NMOS is off and it is 0 means its source is at VDD, right. Its source is at VDD. What is mod of VGS? VDD minus 0 is equal to VDD. So, PMOS is on. So, input is 0, NMOS is, so say input 0, PMOS is on, NMOS is off. So, is there any direct connection from VDD to ground? No, this path is broken, right. And if it is driving another logic gate, so there is no resistive path. What is the between gate and channel? What is there? Oxide, na? SiO2. So, can any current flow through gate? Gate current is Ig is 0. So, no current can flow through this, because this is a capacitive load. That is why in digital circuit you will be always seeing that one cap is drawn at the output. This cap is not there physically. What is there? There is another same circuit, right. An inverter may be driving another inverter or another logic, but what it will see? It will see another capacitance. What capacitance? Oxide capacitance, right. If I am driving another MOS, what I am seeing actually? I am seeing a cap. No current flowed, gate current is 0, through cap also static current is 0. So, from VDD to ground in static condition, is any current flows? No current flows, right, because the path is broken. If this is on, this is off, complementary. Similarly, let us see my input is 1 means VDD. So, what is the NMOS VGS? VDD minus 0 is equal to VDD. So, NMOS is fully on, and let us consider its VGS. VDD minus VDD is equal to 0. So, input is less than threshold voltage of the PMOS, right. You think of mod of VGS, it will be easier rather than considering VSG, you think of mod of VGS. So, if input is greater than VTH, if V in greater than VTH, then only it will turn on, right. If input is greater than the threshold voltage, then only it will turn on. So, when input is 1, my PMOS goes off. See, they are complementary. If one turns on, another is turning off. So, my static current is ideally 0. So, initially when it was developed, people were very happy, because earlier days frequency was much slower, na. So, mostly you can think of it is like a static, right. Most of the cases, for example, you are using your circuit in a digital multimeter or application where the frequency is very low. So, mostly it will behave like a static, right. So, your static power is initially, that is why if you read your books, you will be seeing that CMOS advantage low power, low static power actually. Okay. So, initial applications, if your frequency of operation is low, then it is very good, but as frequency started to increase, then what we see, what will happen? I have a VTC like this, na. When it will reach the middle point, what will happen? both of them will be getting sum of the VTH, right. When this is at the extreme, one is on, another is off, but what will happen when the input is at the middle? So, this is called the short circuit current, right, both of them are on. Then the assumptions we are having that from VDD to ground no connection is there, now there will be a connections, direct connections. So, some power will be drawn there. Another power is charging the cap 0 to VDD, VDD to 0. So, these two will fall in the category of dynamic power, right. So, what are the components? Switching power, short circuit power, glitching power. What is glitch? Glitch is some unwanted transition, we will discuss this later. Okay, this is broadly dynamic power. Static power, can you tell me what are the static power? Suppose input is, you keep your computer on and left it. So, ideally no current, it should not burn anything, but still we burn power, right. It sometimes you will see that you keep your mobile in aeroplane mode, still it is drained, right. So, those are leakage power. So, how it could leak? We discussed about the parasitic diode, if you recall, between bulk connection and source connection, bulk connection and drain connection, right. There will be some parasitic diode which is reverse biased, but even through reverse bias some reverse saturation current will flow, and that is your wastage. So, that is your subthreshold leakage. Even if it is off, suppose your VTH say 0.5 volt and your voltage you are giving 0.2 volt and you are saying that okay, it is off, my input voltage is less than VTH, but still some subthreshold current will flow, right. If we enlarge and check it in the logarithmic scale, you will see that some current is flowing. So, even if your input voltage is less than the VTH, ideally we say that it is off because it is subthreshold, but some subthreshold current will be flowing there, right. What is our current? If you recall that, this is our current, right, ID versus VGS, and if you enlarge this, then you will be seeing that it is not that abruptly at 0.7 it is going off, still there will be some current. Okay. So, if you enlarge this, you will be seeing something like that. So, some subthreshold current will be always there. So, this is called subthreshold leakage. There will be some gate leakage. We are saying that gate current is 0, but maybe some current, small amount, maybe femto, but still it will be leakage. There will be some junction leakage. Okay. So, all of these will combine and make the static power. Clear? So, there are even some subcategories, that is all we consider them as second order effects, that we will discuss in our next class when we will be discussing the device structure. Okay. So, all of these non-ideal effects, that is drain induced barrier lowering, body effect, we will discuss later, do not worry. And we already discussed about this, right, P is equal to alpha C VDD square F. Okay. What is this alpha? That is switching probability. We generally club it with the CL and we call it effective capacitance. Okay. Rest of the term we all know. So, this is actually, this will, if you can address all of these power losses, you are actually entering in your subject, that is low power VLSI design. Okay. You have to think about how we can stop leakage power, then you will be having special design for stopping. See, first our main importance was static power. Initially we thought that okay, we have moved to CMOS, our problem is gone, static power 0. Then you see no, as our frequency is increased, we have a new problem, that is dynamic power. Then we discussed this equation and we saw that if we can scale down VDD, we can reduce down this dynamic power, and we did that from 2.2 volt, from 3.3 volt, 2.2 volt, 1.8 volt, 1 volt, 0.9 volt, and how far you can go. Then the problem of, so first static was dominant, then dynamic was dominant because of frequency. As you try to address dynamic power by reducing VDD, another power became dominant. What was that? Leakage power. If your VDD is close to your threshold, now leakage will be more dominant. most of the time all the transistor will be not strongly off, right. If you have a NMOS of having VDD 1.8 volt and you are giving 0 volt, it is strongly off, right. But if you are reducing down the swing, then it is not that strongly off. Okay. Threshold, this subthreshold leakage will be more predominant. Okay. So, as we are reducing down, now we are saying that even suppose you are working with 0.7 volt. Now, you are saying that okay, maybe dynamic power I am reducing, but leakage power is going up, and there are some other technique that we are following and which is causing leakage power to go up. So, now even the subthreshold leakage or leakage design for low leakage is getting important. Okay. So, this is the beauty of this VLSI design, that it is so dynamic, and if you try to address one problem, another problem will come up. And same thing you will be learning in your analog design course, you will be learning more about trade off. Your professor could be telling you about the trade off. For example, suppose noise you want to, so nothing is free actually. If you want to reduce one thing, maybe some you have to sacrifice something else. So, what is your application, what is your requirement, you need to be very careful. Okay. And all of the game is just for that. So, whatever your customer is asking from you, you should design a thing so that he is satisfied. Suppose some customer he said that I want my battery life to be longer, give me a circuit that will maybe slow, but it should run for longer time. I work out of the station all the time. So, you have to take care of the low power. Someone said I need high speed, I do not care about the I am plugged with my power supply, I work at my home. So, I do not care about the power, as much power it may burn, but it should be very fast. Okay. So, what is your that is your specifications that your customer will ask when you will be joined, and if you are dealing with some customer, you have to deal with these specifications only. He may not be knowing that all this technological term, he will be telling this his requirement. From that you have to frame your technical specifications and you need to give it to your design team. That is why the business run actually. Okay. So, from this we can frame that why we should study this low power design. Okay. What are the challenges, right? So, why should we reduce power? Can you please tell me few reasons why should we reduce power? Think of your mobile phone and just tell. Heating effect, okay. Next, cost, longer battery life, portability. If you have a portable device, some gadget that is not plugged with, suppose PC is plugged with some power, right. So, but if it is a laptop, you may need to carry to your college, and so you need a longer battery life, you need to be lightweight. So, heating is another important aspects. So, all of this will be used for this motivation for designing low power. Okay. What are the disadvantages of heating? Actually, if you think about the circuit perspective, you have done this in your basic electronics laboratory also, that with temperature something changes, right. If you recall, your collector current is getting changed, right, beta is getting changed, right. You designed your circuit for some amplifier with some specification, Q point, load line, if you recall that, and suppose your temperature is changed, beta will be slightly changed, everything will change. Design specification, some technological parameters that is temperature dependent, right, mobility, threshold voltage, all are dependent on temperature, and if temperature is varying. So, when you will be designing, you may have heard this term PVT corner. Have you heard this term? Process voltage and temperature corner. So, suppose you have your customer asked you to design and you asked him what will be your voltage, he said 1 volt, You said at which temperature you will be using this? He said at room temperature, okay, 27 degrees centigrade, and you assume that your process will be typical or nominal, typical, right. Now, after fabrications, all of this can change. When he is running, his voltage may degrade from 1 volt or can 20% degradation you can consider, right. Temperature can change, room temperature can change, process can change. Process means there are generally 6 corners, roughly we say fast, slow and typical. Typical means is exactly what you are designing, but if you are suppose your mobility is getting better, higher, that will be, we will say fast process, your current will be more. Or if your mobility is lower, mobility you understand, mu n, right, ID is equal to half mu n Cux W by L Vgs minus Vt whole square, that mu n mobility. Okay. So, if this mu n is typical, means what it should be, that is we can say it, this process is typical. If it is more than that, we will say that it is fast process. If it is less than that, we will show it slow process. So, what is actually happening? My I is getting changed, I have no control, because I do not know at which process technology it will be come after the fabrication. So, this may change, process may change, temperature may change, voltage may change. So, you as a designer, you have designed for only these 3 corner, and after you have passed the design, the customer is coming back to you and saying that it is not working. It may happen. Then what you should have done? You should, this is your central design, or for all the variation you have to consider it should work for all the corners. So, your job is not done if you just pass it for this PVT. No, you have to make it rigorous. You have to consider all the worst possible condition where it will be function poorly. That should also pass his requirement. Some of the specs will give you worst performance, that worst performance should pass the requirement that the customer is asked, because he do not understand this technical, all these terminologies. He will just see that his things is working or not. So, challenge is on you. When you will be joining a company, these are the things that you will have to deal every day. Okay. So, the user, end user, he could be a layman, he do not know these terminologies, he do not know PVT, what is PVT. If you ask him, okay, what will be your, which corner it will be mostly, no. You have to give him a design so that you are at the safe side, right. So, these all challenges are there, okay, and that is what make it so much interesting. Okay. So, there are certain way of designing low power technique. There are several low power design techniques. For example, we can scale down supply voltage, that we already discussed. We can use multiple threshold voltage. Okay. Generally, we have heard of only single VTH, typical VTH, but we can have a low VTH, we can have a high VTH device. For higher technology, modern technological device, for example, 40 nanometer, 20 nanometer, they have 3 type of device. NMOS having the typical VTH, having the low VTH, having the high VTH. You have the freedom to choose between this. So, if you want to reduce low leakage, what you should choose? You should choose high VTH. If you want a faster circuit, you should choose low VTH. If you want a safe design, you should choose typical VTH or standard VTH. So, you have 3 combinations, permutation and combinations. Now, you will combine with them and check that which is suitable for your applications and so on. So, these are all will come in the low power design technique. You have to play with this multiple VT and with specs, which block is critical, falling in critical path. If I make it even high VT, it will even get more slow. So, those things you have to consider as a designer. Okay. Then what I told you about technology, you can reduce the gate oxide capacitance, okay. By using superior technology. You can reduce signal activity, that is alpha. I told you about different algorithms so that your switching activity is reduced, that you can do. I told you about using parallel, breaking a bigger block into smaller blocks so that your effective capacitance is less, that you can do. Okay. So, these are few of the techniques that we will be discussing later. So, I am just giving you hints, I am throwing you some lights randomly, so that you get the feelings of the subject and you get interest. So, this is actually this modern IC. What is this modern IC? They look like this, looks like this SOC. You may have heard this term, system on chip. Okay. Previously, we were having system on board. Okay. On the board, you have several discrete component, discrete ICs and connected on the PCB, printed circuit board. Now, the same functionality we are trying to bring down the board itself in a IC, that is a system on chip. This could be a memory, this could be a say processor, this could be a amplifier, this could be a LDO, all of this stuff together. Okay. This could be a say antenna, and this could be a transmitter, this could be a receiver. So, all of this a complete system on a chip, single chip. Okay. So, this increases the complexity and challenges. All right. So, if you think about a company's point of view, suppose there are two rival companies and each one is planning to launch a new product next December. All of US companies, US based companies or European companies, they try to capture the market before Christmas. In Indian companies, they try to capture the market before Diwali, right, Diwali or Puja vacations, because people buy more product during that festival time, right. Festival, you see festival and your VLSI, they are such a way clubbed. Okay. So, now you have a window. So, from this onwards, your top management, they decided we will be launching this product, this is the specs, and they give the project to the design team, that you start your design. The design should be ready on silicon, so that we can sell the product early December onwards. And if your window fails, suppose rather than December, you come up with your product on January. So, your rival company will by that time will capture the market, very competitive market. So, you can understand that design window is so important. Same for you may say that for academic it is not that important, it is also important. Suppose you are planning with a idea and you have a plan that this is a new idea, I will be fabricate this IC, I will then publication, I will go for publication for this idea with the test result. Suppose you have targeted for 2 years, and just at the last month of your work, you will be seeing that another researcher with the same idea, he has published same idea, someone may also parallelly they may got, right, they may also get, and suppose he just published it the few months before you. So, your 2 months effort is just gone. Now, the idea is no longer is your, although you started with same, but he produced before you, right. So, this is equally important for industry as well as academics. That is why we said that we should maintain a proper time budget. Okay. Time budget is very crucial, this window is very crucial. Okay. And to reach that window, in each steps I told you, each step you should do a verification is very important. Okay. You have manpower allocation, how much manpower will be allocating and so on. All right. So, let us stop up to this and we will discuss from this onwards in next class.